This is CIT 1122, Module 1, Section 2, Configuring Switch Ports. This gets into some basic configuration about switches and the interfaces that we're going to be plugging stuff into. The first topic that comes up in this particular section is setting up something for duplex. When they talk about duplexing on a device, it just means that you can send and receive information at the exact same time. So in the good old days of network communication, it was a half duplex situation where you could either send information or you could receive information. So you couldn't do both at the very same time. Long time ago, switches came into presence, and switches were able to actually take the information that was being sent and channelize it essentially into a couple of cables and separate it from the data that or cables that were going into the device. So there was the ability to separate those, which we call microsegmentation, which allowed for that bidirectional communication. So you could send and receive. So when someone says how much bandwidth do you have, bandwidth means how much stuff can you send at any given point. And when they say throughput, it means how much can you send and receive at the same time. So devices that are full duplex have twice the bandwidth as a device that has a half duplex situation that could either send or receive at any given time. So most Ethernet installations, cabled Ethernet installations, are full duplex at this point. So you can send and receive information at the exact same time. Now, one of the other technologies that you may be checking into for your switches is how the speed or the bandwidth itself. And most switches will either be set to 10 or 100 or 1000, and they'll auto detect how fast the other device is sending that information. So speed can be identified per port, or it could be set for the entire device. The Cisco devices are set per port. So if you have two interfaces that are connected to a switch and they're both set auto detect that the devices can send at 1000 megabits per second, they'll both be set to 1000 megabits per second. If you wanted to send stuff from or information from some port that's at 1000 megabits per second to some port that's at 100 megabits per second, the switch will receive the information at 1000 megabits per second. It will then buffer, hold on to the information that it wants to send out at a slower interface at 100 megabits per second. So it'll still receive it at the same rate. It'll still be set to 1000. But when it pushes it back out, it can only go at 100. So if you're receiving 1000 megabits per second, you can only send them out at 100 megabits per second. You're obviously going to have more stuff than you can send. You're going to be getting more than you can give at any particular moment. So the switch will buffer or hold the information in its memory, and it will push it out at the speed at which it is acceptable to send it back out. Okay. This is a really cool thing about Cisco switches. There are other switches that will just automatically just downgrade all the interfaces to the slowest interface, so it doesn't have to use any memory buffering. But memory buffering is something that does occur oftentimes when you're going from a faster interface to a slower interface. And that's kind of just what they're getting into here. Every once in a while, you'll run into problems with this, and you'll have to hard code the speeds of an interface. But most of the time, the auto setup is usable and functional. You don't have to worry about it too much. It'll just auto detect how fast the card is on the other side, and it'll set to that particular speed. So that's what they're getting into in that slide. And this just shows you a nice slide on how you can set that up. You see the configuration there. You can do that in a lab as well. And then the next technology they talk about in this section is called Auto MDIX. And Auto MDIX basically says this, that we kind of mentioned earlier that there are cable inside of an RJ45 jack on a Cat 5e, Cat 6, Cat 6e cable. There are 8 tiny little wires, and those 8 little wires have different jobs. In most full duplex solutions, 4 of the wires are reserved for sending, and 4 of the wires are reserved for receiving. Now, think about it this way. If you took your sending wires and you sent them to another device and they were pointed to the sending locations on the receiving device, the technology wouldn't work. So what you would do is you could take the sending wires and then cross them over into the receiving positions on another device, and then that would actually make it function. So you can have something called a crossover cable if you wanted to have direct connection between two different devices, because the sending pins on one device would be hard-coded into the receiving location, into the receiving pins on the receiving device, and vice versa, and you would have direct communication without a switch. A switch, on the other hand, will automatically receive its receiving pins are what would normally be a sending pin for a particular device. I hope I'm not going around in circles. And it'd be nice to draw a picture here, but I draw a picture in another video, so I don't want to get too deep into it here. But what AutoMDIX says is this: there's two types of cables, straight throughs and crossovers. If you use a cable at the wrong time, if you use a crossover where you're supposed to use a straight through, or use a straight through where you're supposed to use a crossover, your send and receive pinouts will be incorrect and it won't work. So what AutoMDX basically says this is it can sense if the pinouts are not correct, and it will then reorganize the pins for receiving. So if you're sending on pins 1 and 2 to another device, and it's receiving those on pins 1 and 2, those 1 and 2 would normally be used for sending. AutoMDX will say, okay, well, I know we normally send on these, but right now we're going to receive on those, and we'll just receive on some other pins, maybe like pins 3 and 6. So AutoMDX is going to fix that so that if you use the wrong cable, if you use a straight through where you're supposed to use a crossover, or if you use a crossover, you're supposed to use a straight through, AutoMDX will solve that for you, and you don't even have to use the right kind of cable. So keep that in mind, and that's what AutoMDIX does. It is turned on the newer versions of your Cisco switches, and by newer I mean over the last 6, 7, 8 years, AutoMDX is going to run by default. However, and we did that in the hardware lab, you should use a straight through when you're supposed to use a straight through, and you should use a crossover when you're supposed to use a crossover. And just to clear that up, when do you use a straight through cable? And the answer is this: use a straight through cable when you're connected to a switch. You have a device that is not a switch connecting to a switch, that's a straight through cable. When do you use a crossover cable? You would use a crossover cable when you're going from one switch to another switch, or when there are no switches, you're going directly from a non-switch device into another non-switch device. Those would be the times you would use a crossover. So there's 3 scenarios: switch to switch, crossover; non-switch device to non-switch device, crossover; or non-switch device into switch device, straight through. In most cases, it's a straight through, even though it's one of the 3 scenarios. It's also the most common scenario. So straight through cables are a little bit more prevalent. In the classroom, if we ever get to go back into the classroom, the straight through and crossover cables are separated based on color. Our straight through cables are yellow and our crossover cables are red. So when you need to use a crossover, use a red cable. When you use a straight through, use a yellow cable, and you won't have any problems. If you find that things are not working and you're not sure why, just switch the cable, see if it starts working. So also, most of the equipment that we do have in the classrooms is AutoMDIX compliant already, and it will figure it out for you even if you do it wrong, which as an instructor watching people do labs incorrectly is very annoying. But it will figure it out on its own. Okay, so that's what's going on there. This slide just talks about the idea behind the running configuration, and we went through this really in the first part, and it just shows IP address information, if there's interface configuration, so on and so forth. We'll get into that deeper in some future presentations, because we have a whole lot to talk about as far as VLANs and inter-VLAN routing in this class. And show commands are a really, really great way to see what's going on your device, especially when you set it up incorrectly and you have to troubleshoot it. So show commands are really good friends, and that's what they're getting into there. It's just a little bit more of that, more show commands, and then it gets into problems that you could be running into. What kind of problems could be run into on a switch? And this just talks about the idea behind input errors, runt, giants, CRC errors, collisions and late collisions. So we're going to kind of finish the chapter here, or the section, talking about input errors and runts and giants. One of the biggest input errors that you'll encounter is that an interface is just shut down. It's not turned on, and you'll just have to turn that on, and that's kind of a big deal. And the light on the front of the device will lead the way as to whether or not the interface is turned up or not. Runts and giants are errors that occur usually because the network interface card is set incorrectly or is malfunctioning. So a runt would be a protocol data unit that is too short to send any data, essentially. When you think about a protocol data unit, there is a data section, and then there are headers. There's a frame header, a packet header, and a segment header. And then the data after that is designed to be used based on the header information that's read in front of it. If the protocol data unit is just too short, if there's no room for any data, it makes no sense to send it at all. It's like sending an envelope with an address in the front of it and nothing inside. So that's kind of the idea behind what a runt is, and that's usually a malfunctioning card is what you're going to find when you're seeing runts. Giants it could be a misconfiguration. Ethernet packets are generally set. A protocol data unit is usually no greater than 1,518 bytes. Inside of that, the data section plus the headers in front of it, 1,518. So in class, I usually say about 1,500 bytes. You should have learned that in 1121. However, in certain circumstances, as if you've got a closed system and you know that you can successfully send protocol data units that are much greater than 1,500 bytes, you can do that. So if you know you can send 10,000 bytes at a time, or 15,000 or 100,000 bytes in one protocol data unit, it'll get accepted and it'll get translated and it'll work. You can crank the maximum transmission unit up to a much higher number, and that will cut down on the amount of headers that you have to send, which will in turn cut down on the amount of overhead on the network, which will in turn make the system faster. But if one device is set to send really big protocol data units and one is set to only receive at 1,500 bytes, then you're going to have a miscalculation. You're going to have a problem, and you get what's called a giant, which is a really, really big protocol data unit that won't be accepted by the receiving device. So keep that in mind. And then the third one, CRC errors, cyclical redundancy check errors. When you look at a protocol data unit and you see the headers in the front and the data at the end of the data, there is a little checksum. And it's nothing more than a value that says this is supposed to be this many bytes. And that's what the CRC check is. So when it's read, if the amount of information that's received differs greatly from the checksum at the end, then the packet is dropped. And that's usually due to fragmentation or some kind of electromagnetic interference, some kind of issue on the LAN itself. So a lot of times you can revert those back to some kind of physical malady on the network, and that you could fix. So it could be external electricity, so on and so forth. So keep that in mind. And then the last couple of things they have on here, output errors. I'm not going to talk any further on those. But the very last thing is collisions. And the great thing about switches is that the collision domain for a particular device that's connected to a switch is just itself. So all devices that are connected to switches can send and receive in full duplex. And they don't have to worry about another device sending them information while they're sending out information. It's not going to collide. It's not going to cause an error. So in a half duplex situation, you would have a collision where a device would have to check its line. And we can get into CSMA-CA, collision avoidance versus collision detection, in another program, but it's not really, this particular presentation doesn't lend itself to talking further about those. And we just talked about those, and we just talked about those, and this just gets into a little bit about troubleshooting. And that takes us through really the second section of Module 1.